Hello students, in this video we'll see an example of a related rate problem that involves pouring water into a triangular prism. Let's consider a tank and here's what the tank looks like. So the tank looks like this. So this is not this, a little bit not to scale, but what we're going to do is we have this triangular prism, right? So I have a triangle over here, and then I just parallel translate it back. And so I have this tank over here. Let's assume that the height of this tank is 6 meters. And let's assume that both those things, I'm drawing this not to scale, let's assume that that's 4 meters over here and that's 4 meters over here. So the top is a square, basically. So we have a square on top over here. That's the top of my tank. And then what I start to do is I start to pour water into this tank. So this is a triangular prism. There's my triangular prism. And so what? And so now I start to pour water into the tank. So I pour a whole bunch of water into the tank, right? And then we make the observation, so the area of the surface area of the water that you see, the surface area of the water is increasing at a rate of 0.8 meters squared per second, or minute, whatever you want the time scale to be. Remember that area is a what? Area is a meter squared, so the units are important there. I want to find out, so let's call this the height over here. That's the height of the water. So let's find out how fast the height of the water is changing. Question. How fast is the height of the water changing? I'll give you a time in a second. So let's first observe that there's a relationship between the heights over here. So what we have over here, let's look at this triangle configuration. So our triangular configuration looks like this. There's the triangular face. I know by assumption that this is what? This is 4. And then the height of this triangle over here, the total height is what? Is 6. And so now if I draw this triangle over here, I like to know this. I know the height is what? I know that height over there is h, right? I like to find this length over here. Well, these triangles are similar, right? So let's call this value x. What do I know about x? So by similar triangles, I know that x over 4 has to be what? Has to be h over 6. H over 6. So that tells me what? That tells me that x is 2/3 of h. So my x is 2/3 of h. So of course, what's the surface area? What's the surface area? So the area formula over here is this rectangular area. So what will it be over here? Well, it's going to be what? It's going to be that x value that corresponds to the height of h, right? And so the area is going to be x times what? X times 4, but we know that x is 2/3 of h. So this is going to be what? This is going to be 2/3, this is going to be 4 times 2/3 of h. So that's 8/3 of h. And now I can take the derivative of both sides of the equation, so I have dA dt is therefore equal to 8/3 dH dt. We know that dA dt is what? By assumption is what? It is 8 meters per second. So this is 0.8 over here. So this is 0.8, and 0.8 is really the same as 4 over 5 is equal to 8/3 dH dt. And so if I cross multiply, that tells me that dH dt, how fast is that height changing? dH dt is going to be what? Is going to be 12 over 40. 12 over 40. And of course, we can cancel some things out. I can cancel a factor of, I have a factor of 4, so I can say that that's 4 times 3. That's going to be a 3 over 10, or 0.3. And this is a what? This is going to be a meter per second because it's a change of height. And so 0.3 or 3 meters per second is how the height is changing when how the height of the water is changing at that moment. Thank you very much.